In this demo, we'll be talking about GUPS. GUPS is an industry benchmark designed to torture test computer systems using random memory accesses. We begin by cloning the source code from GitHub. Let's take a look at the code. This is standard C++ code annotated with OpenMP directives. We build this using standard tools like CMake, and all we have to do is point to the NextSilicon compiler. This compiler is very close to plain vanilla LLVM with some minor additions that export important metadata into what we call enriched binaries. Now that this has been built, we can run it on the host, and NextSilicon detects what we call the most likely flows of the application and immediately prepares them for future acceleration. Note the low score that was obtained on the host. This stems purely from its limited 8 channels of DDR5 bandwidth. Next, let's dive a little deeper to see how this all looks in NextSilicon's profiler. Since this is a smaller application, the entirety of the detected code will run on the dataflow grid. We call this a mill core, a software-defined processing unit created at runtime. There are 192 duplications of this mill that will be made available for enhanced parallelism. We can get a better sense of this by looking at the spatial representation of the grid. In the upper left corner, we can see the data flow expression of a single mill duplication. The shaded areas represent the other 191 duplications taking up the rest of the real estate in the grid. This is probably a good time as any to explain what makes up grid parallelism. A single mill duplication exposes what we refer to as data flow parallelism. And imagine a single thread injected and executing through the projected graph, one cycle at a time. Although there's technically nothing wrong with that, it makes very little use of the available resources. But now imagine that we continue injecting additional threads, which start forming a long data flow pipeline. So eventually we fill up the thread capacity of the mill when every ALU in the mill core does meaningful work every cycle. This is the key concept of how we express parallelism in a data flow architecture. The mill duplications, on the other hand, represent a more traditional notion of parallelism. Each duplication can be injected with up to 512 threads, and all duplications work in parallel, amplifying the rate of execution according to the number of duplications. Next, we click on the mill to examine it in greater detail. On the left side, we can see the control flow view for the accelerated code. We call these interconnected shapes CGs for compute graphs. Some CGs are prologues, epilogues, inner or outer loops making up the mill. Again, in this simple application, all CGs were placed on the grid. In the middle, we have the source code view. The highlighted code represents the code behind the different CGs. On the right side of the screen, we can see the breakdown of individual selected CGs into more detailed graph form. We can look even closer by clicking on one core operation that takes place inside the GUPS mill, the atomic update of the table. This navigates to a specific node within that compute graph, and we can in fact see that the atomic operation is at the core of this compute graph as well as on the source code view. The profiler is a powerful tool that helps developers better understand the operational characteristics of their code. Now let's rerun GUPS, this time on the device. We'll increase the problem size from 256 megabytes to 64 gigabytes, since Mav-2's performance is ludicrous comparing to the host system here. We can see the figure of merit reflected for the acceleration provided by GUPS's mill running on Mav-2. The new score is upwards of 30x that of the host. Going back to the profiler, we can inspect the application again, this time with the added layer of telemetry. We'll start at the timeline view. Here we see a more traditional view of application execution, starting with process creation, moving on to memory migration, after which the mill is executed. The 192 duplications of the mill on the grid are injected with over 64,000 threads. These grid threads execute for just over 1.1 seconds before mill execution is complete. Later, execution resumes on the host, after which the application terminates. Going back to the mill view we've seen before, we'll introduce load telemetry to the control flow view. The load telemetry counts full executions of a CG. We can see that the head CG has a load of 64K, reflecting the total amount of injected threads, each executing it exactly once. Down below, we have the CG highlighted with the red halo, indicating that this is the most executed CG, or the innermost CG, which had around 34 billion executions. Next, in the source code view, we'll turn our attention to the memory access. We can see that the cache hit rate for this particular memory node across all duplications is around 0.4%. Clicking this inline telemetry leads us to a more complete view of memory telemetry for this specific access. Here we can see the cache and TLB hit rates and other pieces of per node memory telemetry. Finally, for this demo, we'll explore the global telemetry view. On the top left, we have the throughput view. In this view, we can see how the average duplication throughput ramps up as threads are injected. Throughput stabilizes around 11% per active duplication as all 192 duplications continue humming along. Later, as some duplications start terminating early, the remaining duplications experience less resource contention. In this case, the resource in question is most likely HBM. These remaining active duplications experience short but measurable increase in throughput before finishing up and terminating grid acceleration. Next, on the right, we can see the per node cache hit rate for all 192 duplications. While this is visually noisy, the key takeaway here is that we do in fact collect personalized cache hit rates for each deployed memory node. Below it, we can see the power usage reading throughout the run, which is rather low for the result we obtain. And last but not least, we have the HBM bandwidth view. Here we see that during execution on grid, we measured active HBM bandwidth of 4.1 terabytes per second. To our knowledge, this is the highest single chip score for GUPS that was measured to this date. This concludes this first demo of going from zero to accelerated execution on NextSilicon's Maverick-2 ICA accelerator. We hope you enjoyed the show, and we'll be back in the future with deeper explorations of other applications running on this new architecture.